non-ionizing radiations. Now, I think you're aware of, last time we were talking about visible radiation, we talk about infrared, we talk about UV, and the non-ionizing radiations. We group into three main regions. Okay, the first one is ultraviolet radiation. Right, this is UVC, UVB, and UVA. And the second one is the visible radiation. This is that you're aware of wavelength that our eyes can see, especially those with colors. Okay. Beyond that, we have infrared radiations. Of course, we cannot see the infrared radiations. And that one's actually, we have a wavelength greater than about 750 nanometer onward. And then you have far infrared telecommunications is around 1,200 to 1,500 nanometer. Okay, that's beyond our scope of course today. Okay, and this is just a simplified in graphical illustrations. So you see the UVC, right? Below 280 nanometer. You have UVB. You have the UVA, all right? And then next to UVA, you have the visible radiations. So roughly around 400 to 700 nanometer. And you have the infrared. Okay. I quickly go through this slide. And basically, when we talk about natural radiations, the solar spectrum itself, right? The solar spectrum. Last time we talked about white radiation, which is we have very broad wavelength. So if you measure or if you can actually obtain the whole radiation wavelength, you have a flat line from UV up to the infrared. Okay. Now, basically, we get most of our natural radiation from our sun. This is what we get even today. If you look at outside, very bright. This is very broad radiation from the sun, but unfortunately, not all the radiation actually reach to the surface of the Earth, and some of it actually being screened by the ozone layer. So we are lucky that all these ionizing radiation or harmful radiation from the sun being blocked much further away from us before it reach the surface of the Earth. Okay, so this is what happened in the ozone. I just quickly go through. You have the uppermost layers, which is from 10 kilometers to 50 kilometers. And then you have the troposphere, which is, well, if you are on a plane, you travel within this range from the surface of the Earth. In between, we have some kind of we call it the ozone layer, where the ozones are. So basically, the ozones, if you look at the reaction of the ozones, we take the illustration on the right-hand side. All right, you can see here illustration on the right-hand side. So the light radiation from the sun, right, will be absorbed by the oxygen molecule. So what you have is basically the radical of oxygen, so 2O. So in this illustration, there is no indication of the radical. So if you return just a single alphabet O here, so you assume that it is a radical, right? And then, of course, this lead to eventually the formation of the O. Right, just quickly. Right now, the Planck equation. If you look at the Planck equation, basically this one is describing the how we calculate the energy of radiation. So we have E, and H is the Planck constant. So this constant, I think, much better you remember. I think by now you remember them, all the constant that we have, right? The speed of light. So this one is round off to 3 times 10 of 8 meter per second. The Planck constant is 6.63, 10 minus 34 joule seconds. So this energy of radiation, basically, you can determine in the form of electron volt or in the form of nanometer. So if you go along from UVC to infrared, so you actually start from low wavelength, 200 nanometer, let's say, okay, and you're moving up to 300, 400, 500, and 700 nanometer. So the higher the wavelength you go, the lower the electron volt energy by this calculation. Okay, that one is simple, and you know about this E equal to Planck constant time. Okay. Now, the 1 electron volt equivalent to 1.6 10 to the 9. So this is, you've seen it before, right? So if you look at the energy, right, the mu, actually the speed of light over the lambda, yeah, you plug in all this value. Okay, you take an example here, we have 650 nanometer. Okay, energy, maybe this one is lambda max of emission or lambda max of absorption, right? And you end up having a value in electron volts, right? In this case, in our example here, is but 1.91 electron volts. Okay. This is a simple calculation. Okay. Got that? It's okay, isn't it? Very simple. So the electron energy that we mentioned in electron volts, if you are carrying out a research in, well, we talk about solar energy, for instance, harvest solar energy, you may use organic dye molecule or something, vitamin K, vitamin E. You can use any organic molecule that absorb light energy. Now, typically, this molecule will have delocalization of electron or to p orbital, right? P orbital. So those double bond, triple bond, right? They basically absorb light energy. Okay, and later on, I think one of the slides we are talking about benzene, so we discuss on that. Okay. And remember we have h mu just now. So the mu actually c over lambda. So the speed of light divided by the wavelength of the energy, you end up having the electron volts. So you can have the in the form of joules, for instance. Right? It can depends on what you ask to do. Okay. Else, I think in the typical photochemical processes, if you are looking or if you are measuring how much energy being harvested from the sunlight or from light that you are pumping into your system, so you are not actually telling the audience you are having energy in nanometer, but you are telling having energy in joules, or you're telling the audience how much storage energy you have harvested in the form of electron volts, isn't it? So it's much easier, okay, for the audience to understand. Okay. Okay, moving on. Okay. Now, this is just what we are discussing, so you can read through. Okay, and I mentioned a little bit. I just did not read my notes on your screen. I just mentioned earlier. Okay, it's not that much. Because I transfer from my PC to my tab, so there was change in the format just now. Okay, let me see. Sorry about that. Okay, basically when you never mind, forget about not seeing the Jablonski diagram. The photophysical processes. The word is photophysical processes. We're not saying photoorganic, right? Photophysical, photochemicals, right? So anything about when you talk about photo lights, this is physical processes, right? Basically, we are talking about electromagnetic radiations, right? And during these processes, normally you don't have bond breaking, bond making, or something, right? So the molecule actually remain as molecule, just like the Frank Condon principle said. What we have is just it become excited, it absorbs the energy of the light, right? So if you compare to photochemistry, right, you have maybe bond making or bond breaking. We gave example just now, the ozone formation. Yeah, you have light energy absorbed by the oxygen molecule, and oxygen molecule become, one single oxygen molecule become two oxygen radical. Right? This is photochemical processes. Right? And it said here, photophysical processes include the light-induced generation of excited state, transition between the excited state, relaxation, and then return to the ground state eventually. In the process, the molecule may be transferred from ground state to excited state. So the transitions can be observed by us using instruments such as spectrophotometer, right? If it is actually emitting from triplet state, you use fluorescence spectrophotometer. Right? Um, you can, during my time when I did my degree, one of my research was I determined the triplet state of the molecule that I studied using a laser, right? So I map out the singlet state as well as the triplet state of the molecule. So I get exactly what is the energy from S0 vibrational state to the first electronic excited state, as well as I determine exactly the lowest excited triplet state. Since I have the ground state energy, so I can actually map out the whole Jablonski diagram. Okay. Right. So I think I have the next slide. Oh no, it's not something. Let me see whether I can draw it here. I can put it. The one not able to go back to the screen. Now, what is Jablonski diagram? Now you should be able to draw Jablonski diagram. Okay. Now, a molecule, right? You have an atom has nucleus and you have electron, isn't it? It's orbiting about the nucleus. Right? When we talk about molecule, it's made up of more than one atom. Okay, and normally the one that absorb light energy, mostly they are, those molecules that have pi electron, the 2p orbital. So the electron will delocalize about the molecule. So those that molecule that has aromatic molecules, unsaturated molecule will this. Okay. Now, if you take this is a EV, for instance, right? So this is S naught, and remember, depend on the state of the molecule. The molecule have, all these rotational, vibrational, first, second, third vibrational energy level. So if you take this one as the excited vibrational state, okay, and remember there are other energy level, okay, and you have this energy, light energy, h mu, okay, and the molecule I just draw from the ground state, okay, will absorb this light energy and then goes to the excited. This is the molecule, this particular molecule. Okay, I'm not saying other molecules. So this particular. Okay. So in here in the center state, the molecule may relax. Okay, and falls not necessarily over here, but may fall somewhere over here. The triplet state normally has energy lower than first excited vibration state of the molecule. So now I just put it slightly lower. Okay, slightly lower. Okay. Let's say the molecule now is over here. And this is the triplet state also has other energy state. Right. The molecule may undergo intersystem crossing. Okay, right? Intersystem crossing. Of course, it might be very fast. Some molecule could be slow. Depends. So we can determine the rate of intersystem crossing. Right? If the molecule, right, come down to the ground state from the first excited state, right, it emits light. So this emission is fluorescent emission. Okay. Now going back to the triplet state. Okay, it's too far on my left screen. Okay, intersystem crossing, it also undergo relaxation as well from upper vibrational energy levels or alpha level to the lowest state of the triplet state, lowest energy level of the triplet state, sorry. All right. And from here, right, the molecule eventually come down to ground state because this is the most stable state of a molecule. Okay. This ground state always have some Boltzmann constant time. You can see my screen, right? So Boltzmann constant time, absolute temperature. Okay. Anybody coming in? Let me know. Okay. Because on here I'm too focused on the screen of my tablet, I don't see you is coming. Okay. At any particular time, our molecule have this energy. So in the ground state. Okay. So just in case any of you try to contact me. No. No one. Okay. Right. Now, as this molecule coming down to ground state from the triplet state, right? This is phosphorescent stage, huh? Phosphorescent. Okay. So fluorescent, phosphorescent, right? This is the photophysical process that you may observe, right? As a result of molecule absorbing light energy. So this diagram is Jablonski diagram, right? Okay, you can draw that, isn't it? No? Yes? No problem. Okay. Oh, still there. Okay. Now I basically describe all the photophysical process, including the absorption and the emission. Okay? Very simple one. Okay. So this one is another way of drawing your Jablonski diagram. Okay. So this is on your right hand side. The drawing of energy level actually in a curve, right? There's a certain profile, okay, and potential energy is the same like we did, right? And then you have the bond interval, which means the distance between the two molecules. Okay, if the molecule actually undergo a reaction. Now, this plot of energy level is just like TBLO main diagram. Okay, the resultant profile as you add repulsion energy, okay, which is in the upper quadrant, which is positive, with van der Waals energy, which is in the lower quadrant, is negative. Van der Waals is attractive, right? Repulsion energy or electronic or Coulombic repulsion. What is repulsion? Is repulsion, it repel each other. You add them up, you get this, right? Basically. So it's almost similar, right? Almost similar. So as you're moving from right, right to left, right? This is actually as a molecule approaching. Okay. Right. Clear? No problem. Okay. See that on my screen. Yeah. Just now I saw like 23. Now I have 22. Any of your friends missing? Somebody or somebody writing, huh? Just a minute. Okay. Now the person is in. Just a minute. I'm just checking your attendance. Okay. Shakila Rosli, yeah, just joining our class. Right. So we have 23, so 21 of you. Right. Want to confirm your attendance. Is that on the screen? No. Okay, I'm just checking. You can write notes if you like. Okay, so that I can see it from my other computer. Okay, because my tablet actually covered the whole computer screen. I don't see you. Okay, just so that you know my situation over here. But I can see you, right, from my other computer. Okay, right. You can open your uh, camera. It's fine. Right? You can raise hand. You want. You can, or if you don't want to raise hand, you ask questions. You just write notes, right, on your right screen. Okay. Right. Um, Before I came into the class, I just added from the website, right? Wikipedia Frank Condon principle. So it's not much. what we want to see here is actually the Jablonski diagram, right? The energy level diagram. So what happened when a molecule, I said a molecule, within one molecule, right? Probability of this molecule, okay, absorb the sunlight and then get excited, moving up to the excited vibrant state, and possibility of undergoing intersystem crossing, right, to the triplet state, and eventually come down to the ground state. Okay, so you notice the diagram that you have on the right hand side, that's slightly lower. Okay, the S naught orbital and all the orbital not necessary the molecule, all right, having S naught at zero ground state. Okay, so almost unlikely you to have theoretically the temperature of the system is at 0 Kelvin, right? At 0 Kelvin. Wow. Right? So you need liquid nitrogen for that. Okay. So at 0 Kelvin. So more likely the molecule at zero energy level. Right? In normal condition, in the fridge, in the freezer, right? It will be somewhere in the vibrational state of the ground state. Okay. So this is what I've described just now. Okay. So, but the illustration that you have, the diagram, just telling you how fast, right? The excitation, absorption. If you look at in seconds, about 10 to the power of minus 15. This is in picosecond, right? This is in picosecond. And realizations, how fast it is internal combustion and propulsion realizations is around 10 to the power minus 11 seconds. Okay. The fluorescence, right? Up to 10 to the minus 7 seconds, 10 to the minus 7 seconds in nanosecond. Okay. This is how fast it's undergo the fluorescence, right? But not all molecule experiencing undergoing fluorescence. If you have 100 molecule, not 100 molecule coming down instantaneously, right? Simultaneously, all together at the same time. Remember, this molecule could be in the air. This molecule could be in the matrix of solid. These molecules could be in the solution, whether it is organic or aqueous solution. Okay, and is subjected to the environment at that particular time, and the molecule may come down at different time, but overall you can see a decay process of the fluorescent or phosphorescent. Okay, what's missing? Okay. Have to take it out from the screen. So this is how fast. Okay, so I'm just going down to the lowest one. A slowly decaying excited species can undergo very large number of collisions within with other reactant before deactivation. So this is what I'm saying just now, right? So the molecule may present in a different environments. Okay, right? So the interplay between reaction rate and excited state lifetime is very important factors in determining the kinetic feasibility of the chemical process. Why we need the kinetic feasibility? All right, this you want to see how fast reaction can take place. You want to see whether is it possible. You want to see whether if you have another molecule, the molecule can um, have time to take the energy out from the molecule A. You have molecule B coming to the excited molecule A. It may have sufficient time to take the energy. Okay. Or else, before it collisions, the energy also come down to the ground state. So wasted. Right? Okay. So just quickly, right? The relation I'm saying just now is non-relative, right? So emissions is phosphorescent and fluorescent, right? Just quickly so that I don't want to finish on that. Sorry, on that screen. Now, this is you may be familiar, right? Now, if you look at the unit spectrum, okay, remember we were in the topic of geology diagram look like, right? You have the left-hand side, which is describing the electron of the field from the ground state to the higher level. And then we're talking about the treatment, right? So the first one, okay, when you actually move from ground state to the excited transition of the molecule moving from ground state to the excited state can be observed using spectrometer. Just like you're looking at last time we're talking about this brown shirt, yellow, blue shirt, and so on. Right? Actually, of your the dye molecules on that so on the fabric of your shirt. Metal actually have, okay, and the molecule actually absorb all the energy except the energy of the color that we observe, right? So we have a much lower wavelength emitting the higher wavelength. They may appear blue. Some molecules has the wavelength, not so much of approximately 600 nanometer, for instance, if the molecule absorb all energy of 100 to 600 nanometer, for instance, it appears to be maybe yellow or it appears green. Okay, so it's for the what you get of the release of the energy you see. The energy you see. So that's it. Okay. So in your laboratory, you do the excitation actually what they absorb. What did they absorb? It has absorption energy. It's the molecule actually needs. Let's say. Okay.
No, your voice is not
Okay.
clear.
No. Yes.
Your voice is not clear.
Yeah.
Your voice is not clear.
My voice is not clear. I think I want to say. You hear that? No?
Yes, yes.
Okay now? So, okay, I turn off the speaker. Yeah? Okay, I presume it's okay. Okay. The assumptions. In order for the equations, this is much higher wavelength. This one is much higher wavelength to each. So let's say to have absorption around the max is 350. Okay. In order for you to use mass energy to the system, maybe yeah, you can 330 nanometer. So energy that you pump into the system. Okay, because you want to observe the emission. Okay, once you pump in this 300 nanometer energy, so you pump in basically 300 nanometer energy. This is energy pump in, okay? Okay, and the molecule relax. Okay, what you're observing for the fluorescent spectrophotometer, you'll be able to observe this part on this. Speed a bit slanting. So this is what you're observing over here. You don't see here. You don't see the absorption spectrum, but you see the emission spectrum. You pump in high energy. If you want to observe the absorptions, you just expose to the light energy, and you observe the absorption spectrum. But the instrument normally can actually work. Yeah, you set the energy here at 450 nanometer. You can determine of your sample, you can get the absorption spectrum. But usable spectrophotometer in your laboratory, you don't have to worry with that because you just put your sample in and it measures actually all this energy absorption of sample. Okay. Right. And this is benzene. Quickly, now it's 9. My watch is, okay, give me a minute. Okay, give you a minute. So benzene, I just draw benzene molecule. Sorry, not very nice. Oh, it's not your screen. Yeah, there you go. Okay, not very nice. So you have this S orbital. Okay, and of course we have the delocalization electron. Right, this benzene molecule. So since it is just one single C6 carbon, right? The absorption energy is much lower in the UV region. Okay, the absorption region. So if you want to get the fluorescence energy, you need to pump in around here. And the fluorescence spectrum as well as the phosphorescence spectrum of your benzene. So benzene normally you run UV visible spectrum. You have this T peak, right? Around 220 to 250 nanometer. Okay. Any questions so far? No? Yes? Okay. Class? Now, how come you have 24? Just a minute, don't leave. Okay. I have 24 of you. Screen record. No. Yeah, 24. I just take your attendance. I don't want to miss your attendance. I prefer to actually screenshot your attendance. Right? So I have your record here. Okay, thank you. Thank you, guys. All right. I think we stop for now. Okay. I see you next week. I think we should have online class like this rather than giving you a video or pre-recorded lecture now. Is that okay?